Okay, let's get started. So we talked about isomorphic scaling, and we finished the process of showing that no matter what the shape is, when you scale it isomorphically, meaning you change all the linear dimensions by the same multiplicative factor, the volume always increases proportionally to the cube of that factor. And the area, the surface area, meaning the part of the object that's exposed to the air, always increases proportional to the square of the scaling factor. We talked about how the heat produced by living things is proportional to the cube of the scaling factor. The heat loss is proportional to the square of the scaling factor. And so that means that the bigger things get, the harder it is for them to dispose of the excess heat. On the other hand, the smaller things get, the harder it is for them to conserve enough heat if we're talking about a warm-blooded animal. And so small animals normally have fur or feathers to help them conserve their heat, and large animals are usually have very little hair. Then we started talking about scalars, which are physical quantities that have only a magnitude, such as temperature, can be positive or negative, but only has a magnitude. And the other kind of quantity that we're going to study in this course are vectors, which have both a magnitude and a direction. So the magnitude of a vector is always a positive number, which in the graphical depiction of the vector corresponds to its length. And then the direction is the direction of the arrow points. So questions about any of this? Okay, I want to remind you, hopefully you guys got my email about the pizza party. Yes, good. So I hope you will come tonight. I'm pretty sure that we're going to be on. We do it even if it's raining lightly. We have a very large open porch with a roof, so it'll still work even if it's raining lightly. So I'm pretty sure we're going to go ahead, but I will send out a final email right after class, after I've had a chance to check the weather one more time. We will have vegan and gluten-free options if you need those. Somebody pointed out to me there's an error in our syllabus. The clinic is, I think the syllabus says that the clinic is on Zoom. That's wrong. The clinic is in person only, and it's in E309. Oh, and I now know what the hours are. I should put those down. So it's tonight, Wednesdays, it's going to be 8 to 10. And Thursdays, it's going to be 7 to 10 p.m. So again, the clinic is staffed by friendly physics majors, and it's specific to just this course. So they are absolutely prepared to help you with the homework problems. Again, you are required to spend 10 minutes per problem on your own before you go to the clinic. Did somebody have a question? Okay, yes.
For the individual problems, I recall you saying that like you can meet with the.
You can only get, yeah, so only if you have a dean appointed tutor or me. All right, those are the only sources of allowed help for the individual problem. So you can't get help from the clinic on that.
So it's dean appointed different than going to like the OAR?
No, same thing. So OAR appointed tutor is fine. Yes. Any other questions about the clinic? Yes.
Another thing, but where are your office hours today?
My office is so Walter is KINSC L110. So the L part means that it's the link which connects between the Harris/Hillis part of the Science Center and the Sharpless/East Wing part of the Science Center. So if you remember where there's sort of a place where you can walk right through the center of the Science Center if you're going down to the campus center. If you go through that side door, my office is the second one on your left. So turn right through that sort of breezeway into the side door, and my office is the second one on the left. Good question. So today I think it's 1:30 to 2:30 is my office hour. And again, I want to emphasize, if my office hours don't work for you, you're very encouraged to email me, and we can set up a time that does work. So, for this week's problem set, this is always happens that the first one I'm never quite able to get through as much material as I want before the problem set. So we're doing some material today that is needed for this week's problem set. Most of the time that won't be the case. Usually we'll be done with the material in the problem set that's due on Friday. We'll be done with that material by the end of the class on Monday. so that you can get an earlier start. And always, we have done much of the material by the end of the class the preceding Friday. So you can always get started on some of the problems over the weekend. Okay, here's where we left off last time. We were talking about displacement vectors and position vectors, and we were thinking about a bug that starts at a position vector r sub 1 relative to the origin. And one thing I forgot to mention was the meaning of this little arrow. So when I draw a vector, when I'm handwriting it, I put a little arrow like that, and notice the typical convention is we don't bother to put the top and bottom parts of the arrow. Just for quickness, we just put the little top part like that. In your book instead, and in most printed sources, the vectors appear as boldface. So they don't have the little arrows above them. So in some ways, it's a little bit unfortunate that there's these two different conventions for handwriting vectors and with how they appear in printed format, but it's very, very universal that they're done that way. Okay. So we saw that we could define a displacement vector R1, which goes from the initial position of the bug to the final position of the bug, R2. Oh, I forgot one important thing. I want to introduce a teaching assistant, Logan, who's right there, and he'll be assisting me and Professor Kazi during the small group discussions. So there's a lot of you. It's kind of hard for one instructor to get around to everybody. So Logan will be helping out with that. And he is also one of your clinic teaching assistants. So you might see him there as well. Which night do you work, Logan? Thursday nights, okay. And one more thing about clinic, tends to get crowded on Thursday. So if you can be organized enough to go on Wednesday, not to knock Logan at all, but it's going to be less crowded on Wednesday. It might be easier to get your questions answered more quickly. But so we have 3 student helpers, student teaching assistants working on Thursday and 2 on Wednesday. But even with that, it's less crowded relatively on Wednesday. Okay, so the displacement vector delta r. So that starts from the initial position R1 and winds up to this later position R2. I could write that as an equation, a vector addition equation. I could say R1 plus the displacement vector delta r is equal to R2, like this. And so this is an example of vector addition. And we can see how it works graphically in this, this picture, which you should have in your notes from last time, that to add things, add vectors, we put them tip to tail. So I put the tip of vector R1, align it with the tail of delta vector R, and then that gives me the resultant R2. So I'm just going to do that again here. So here's R1, and I place delta R with its tail next to the tip of R1, and then I draw the addition of them starting from the tail of R1 and going to the tip of the second vector in the addition, delta R, and so that gives me R2, like so. So what's another mathematical operation we might want to do with vectors? Yes. We might want to subtract them. So let's talk pretty generally now. If I have vector A and I want to subtract vector B, how do I think about that? Well, it's easiest to just add the negative of vector B, which is simply a vector that points in the opposite direction. So let's say if I have vector A is like this and vector B is like this. Most of the time when we're talking about vectors in this course, the position of the vector doesn't matter. The one exception to that is a position vector like R1. So usually the placement of the vector on the page doesn't matter. So for example, the displacement vector has the same meaning whether I draw it down here or some other position up here. As long as I draw it pointing in the same direction and with the same magnitude, it means change from your position here go downward and to the right by such and such an amount. And so that's something that's independent of where that vector is placed. Similarly, for velocity, acceleration, force vectors, which we're going to encounter over the next couple of sessions, where you place those vectors on the page really doesn't matter. So for example, a force vector might point that way, and I could draw it over here, and it would mean the same thing. It means a force that's pointing up in that direction, and the longer the vector, the stronger the force is. An exception to that rule is a position vector like R1 and R2. Position vectors always have to be drawn starting from the origin, but most of the time, the placement of the vector on the page doesn't matter. So back to thinking about subtraction of vectors. If I want to form A plus negative B, first I draw the opposite version of B. So I draw a vector of the same length, but that points in the opposite direction. And then I do the tip to tail addition of the two of them. So if I put them tip to tail, there's my A, there's my negative B, which is meant to be slanting slightly. So that's negative B. And so the resultant is this. So that's A minus B, or A plus negative B. So let's apply this idea right away of vector addition and subtraction to a real life problem that you might encounter. And I think I'll tip my hand a little bit and say you certainly will encounter this on exam 1, which is relative motion. So first we'll do a one-dimensional example, which hopefully you have good intuition for, and then we'll do a two-dimensional example for which you really need to think using vectors. So let's say I have a train car, and it's a flatbed train car, and let's say that it is moving to the right at 50 miles per hour. On the train car, relative to the train car, there is a person, and the person is running relative to the train car at, let's say, 13 miles per hour. Then we have another person who is stationary on the ground and is viewing that person who is running on the train. So what speed does the stationary person perceive the person running on the train as having? Think about that on your own briefly. You should have a pretty good instinct of this. It's not meant to be a trick question in any way. Check your thinking briefly with somebody next to you. Okay, so I think I heard a lot of people saying 63, and that would be correct because they're both velocities are in the same direction. So they say that person is running at 63 miles per hour relative to the ground. So now let's redo the same problem, but we're going to use symbols instead of numbers. So let's introduce a symbol for the velocity of the train relative to the ground. So V sub TG. So this is train relative to ground. And V sub TG would be 50 miles per hour. And let's say that this 13 miles per hour, that's going to be the velocity of the person relative to the train, V sub PT. Person relative to train. And using this system of subscripts, the velocity of the person relative to the ground would, what symbol would we use for that? V sub PG, exactly. So V sub PG, person relative to ground, is equal to V sub PT plus V sub TG. There's a little mnemonic that I encourage you to use to make sure that you've gotten this correct. So in one dimension, it's easy to see because you have good intuition for one dimension. In two dimensions, it can get a little tricky. So the mnemonic is I can kind of cancel out mentally these inner two subscripts, and that leaves me with PG, which is what I want on the left side. So this is a little, just a mnemonic device. Mnemonic, quote unquote, cancel the inner subscripts. Questions? Okay, so now let's apply this to a two-dimensional problem. Let's say we have a ship and it's near the east coast of the United States. So here's a kind of crude drawing of the east coast of the US and part of Canada. And let's say that here is our ship. And maybe the velocity of the ship relative to the ocean is in this direction. So I'm going to call that V sub SO. Ship relative to ocean. So relative to the ocean, the ship is steaming straight north. But it is in a part of the ocean where there is the Gulf Stream. And so there is another vector that's important, which is, let's say, like this. So this is the velocity of the ocean relative to the land. And I'll put a vector on it. Ocean relative to land. And so what would the velocity of the ship relative to the land be? I want you to work on that on your own just briefly, and we're not talking numbers here, just draw the correct vector. So what is the vector for the velocity of the ship? And I'm not going to tell you the subscripts, but you should be able to figure them out relative to the land. Work on that on your own briefly. Okay, check as soon as you feel ready, you can check your work with somebody near you. Yeah.
Oh, right.
Okay, Annie, walk us through it, please. Okay, so what symbol are we going to use for the velocity of the ship relative to the land? V sub SL, and then as Annie just said, that's equal to V sub SO plus V sub OL. And again, using our little mnemonic, we can see that we got it right because we can kind of mentally cancel these inner subscripts to get V sub SL. So that's good. Tell me what to draw now. So that's this one, V sub SO, the velocity of the ship relative to the ocean. So, and then tip to tail. So the tip of V sub SO, I put on the tail of V sub OL. And then we do the tip to tail vector addition to get V sub SL like that. Yes, Vic. In principle, not. So, in other words, I could say that this is equal to V sub OL plus V sub SO. And let's just verify that that's correct. So if I put V sub OL like this and V sub SO like this, then I'm going to get the same V sub SL. So the addition of vectors works in the same way as regular addition, that the order doesn't matter. I would say when you're thinking about relative motion, it will help you to use my little mnemonic. And so in that case, do it in the same order that you write it when you use the mnemonic. Yes, Jean.
Are they viewing the person on the train car like at a constant velocity of 13 miles per hour? Like what happens if the person were to be decelerating or accelerating? How would that affect the like what they do the person just
it would depend. So Jean asked, I think, what if the person who is running on the train is not moving at a constant speed of 13 miles per hour relative to the train, but instead, let's say, is accelerating? So we're going to talk about this more in about 10 days or so, but we can imagine an instantaneous velocity. So at a single instant in time, I can say that person is running at 13 miles an hour. And maybe a second later, they're going at 14. And so the result would change. But at that instant, they're going 13. And so it just still adds up to 63. Yes. I'm sorry, say it again. Do we always draw them? I'm not sure if I've understood your question. Do you mean, is it allowable to draw a vector like that?
Like if you add in the people, instead of doing like, instead of just like writing it from the top of the arrow, if you could
Come up here and show me what you mean. What's your name?
Teresa.
Teresa, thank you.
Like if we connect them like that instead.
Okay, so great question. Teresa, did I get that correct?
Yeah.
Thank you, Teresa. So this would not be tip to tail. This would be tail to tail. So if this is A and this is B, the result, there is no result because I can't draw, I always want to draw the result from the tail of something to the tip of something. So this is not helpful for finding the vector sum because it's tail to tail instead of tip to tail. Does that address your question? Not helpful for finding A plus B. Instead, we would want to draw them like this. This would be A plus B. Great. Other questions? Yes.
What are the added lines?
Once again, a little bit louder. So I was hoping to rely on your intuition from the one-dimensional case, where hopefully it made sense to you that we should add the velocity of this person running to the velocity of the train to get their velocity relative to the ground. And so that gave us this equation, which we are now just generalizing to 2 dimensions, or we could also use it in 3 dimensions. Good. Okay, so far, our ability to add vectors is limited to sort of drawings, but you know in this course that we care about numbers too. So how do we add vectors in a more quantitative way? To add quantitatively, we need the components of the vectors. So this is a new idea, components. So for example, let's say if we're talking about now a velocity vector. So here is a vector that represents the velocity of something that's pointing upward and to the right. So this might be, let's say, my velocity relative to the ground, moving that way. I can resolve that into a part that points exactly in the x direction, which I could call v sub x vector, and a part that points exactly in the y direction, which I could call vector v sub y. Does that make sense so far? So it's a way of breaking things down into their parts along the x and y directions, and I can see, so these are related by a 90-degree angle, of course, because they're in x and y, but I can see that vector v is equal to vector v sub x, the x component, plus vector v sub y, because I've done this arrangement of these 2 vectors, so they're already arranged in the tip to tail arrangement. Yes?
Why can't the overall vector v be tip to tip with the v sub y? If we're specific to tail.
So when we are talking about tip to tail, we mean on the right side of the addition, the things that are being added together should be tip to tail. Great question. Okay, so does this diagram make sense? Questions about this? Because we'll be doing this a lot over this whole semester. Okay. So I'm going to define a new way of writing some things. So I'm going to define v to be, without the vector sign, to be the magnitude of vector v. And the magnitude means the length. So let's say that this is at some angle. I'm going to choose a 45-degree angle just to make it easy. So let's say that vector v represents a motion at 5 meters per second, a velocity at 5 meters per second at 45 degrees. The magnitude of v would be 5 meters per second. So in order to fully specify v, I could either specify the magnitude and the angle, or I can specify the 2 components, right? So in this particular case, I would say v sub x, when I write that symbol, and I've stopped writing the symbol, what does that mean? Louder? Somebody over here was saying something. It's the magnitude of vector v sub x. And in this case, that would be 5 meters per second over square root of 2, because it's a 45-degree right triangle. And in this case, v sub y would also be 5 meters per second over square root of 2. So I could say a few different things. So I could say v is a vector of magnitude 5 meters per second, 5 meters per second, pointing at 45 degrees above the horizontal. That fully specifies vector v. Or I could say v has an x component of v sub x equals 5 meters per second over square root of 2, and a y component v sub y equals 5 meters per second over square root of 2. I would say the first way of specifying the vector is called, I might call it the polar method of specifying a vector. And the second way I could call the Cartesian method of specifying the vector. This is important. Whenever we ask you for something that's a vector, you must specify it in at least one of these two ways. So there's a problem on the homework, for example, where you're asked to give, I think it's a velocity. It doesn't say give the velocity vector, but that word velocity, if you're talking about a two-dimensional problem, implies that we want the vector. So on that problem, I think it's a problem with a bug crawling around. You've got to either give it in the polar form, magnitude and direction, or give it in Cartesian form, giving the two components. And the components can be negative, right? So let's do a different example. Let's say if I have a velocity like this, velocity like this, there's our v sub y vector and our v sub x vector. V sub y would be, oh, I'm going to get in trouble here. I'm using symbols in two different ways. Sorry. The way that we've talked about it so far, v sub y would still be positive, but vector v sub y is pointing downward. So that's not a good example. Forget that. So unless we explicitly ask you for either polar or Cartesian form, you can pick whichever one is easier. And depending on the problem, one of them is usually going to be much easier than the other one. And you don't have to do both unless we explicitly ask you to do both. Okay. Most of the time when we're talking about components, we don't actually use the terms vector v sub x and vector v sub y. So not normally used. I did that for a reason to sort of show that I can form something by adding them two together, but the more normal way of writing it would be, let's go back to this example, vector v, and I'm thinking about the two components. I'm going to define x hat. I'm going to define, so the three slashes and an equal sign means is defined to be, at least in a physics context. I think sometimes mathematicians use that symbol to mean something else. Does anybody know? I don't know. Anyway, in this class, and talk to any physicist, when you have three of those, it means is defined to be a vector of magnitude 1 pointing in the positive x direction. So notice that the magnitude has no units. So x hat is called a unit vector because it has magnitude 1. So that unit means it refers to the magnitude 1. So it's kind of funny that it has no units and yet it's called a unit vector. And similarly, y hat is a vector of magnitude 1 that points in the positive y direction. So I could write this vector here that represents the x component of vector v. I could write that as a magnitude v sub x times, times x hat. And I could write this one as a magnitude v sub y times y hat. And then I can write vector v is equal to v sub x times x hat plus v sub y times y hat. And I just did something that I kind of slipped under the rug, which is how do you multiply a vector by a scalar? So like here, I've got x hat and I'm multiplying it by something that doesn't have a vector sign, so it's a scalar. And how do I do that? Well, the same way that you multiply anything. So let's say if v sub x is 1 meter per second, then I would take that 1 meter per second and multiply by x hat, and that would give me this vector that has a length of 1 meter per second, and it's times x hat. If instead v sub x were 2 meters per second, it would just be a vector that was twice as long. 2 meters per second times x hat. So I'll be able to talk about that a little bit more in just a couple of minutes about how do we do scalar multiplication. But for now, we'll settle for that kind of semi-intuitive definition. So this is the more common way of writing a vector in terms of its components. And when we write it this way, we allow Vx and Vy to be negative. So for example, if we go back to this example like this, where let's say we have a different velocity like this, and I've got the x and y components like this. Now Vy is less than 0 because this is a vector that's pointing in the negative v direction, but Vx would be greater than 0 because that component is pointing in the positive y direction, positive x direction. Questions? So let's do an example that kind of combines all these things. Let's say, so example, let's say that the velocity of, let's say there's a bird. That's my way of drawing a bird. And the bird is flying in your backyard relative to the air, right? The bird flies through the air, sort of like a ship goes on the ocean. So this is the velocity of the bird relative to the air. And then maybe the air relative to the ground is like this. Air relative to the ground. So this is bird relative to the air. So this is bird flying in your backyard. And this is the air relative to the ground. And we're interested in what is the velocity of the bird relative to the ground. So it's the same problem really as what we did with the ship on the ocean, but now we're going to have numbers. So let's say that VBA is equal to, let's say maybe 3 meters per second times x hat plus 2 meters per second times y hat. So if I were to draw the VBA vector, that means that I could resolve it into its components like this, where this horizontal component has a length, quote unquote, on length. So we're representing a speed by the length of a vector of 3 meters per second and a vertical component of 2 meters per second. And we could, yeah, let's just leave it there. And then let's say, so given that and given that VAG, so VAG, let's redraw that. That's kind of pointing downward and to the right. So which component of VAG is negative and which is positive, or are they both negative, or are they both positive? Yes. Nope. Try again, because it's pointing downward and to the right. Somebody else? You. Yes, y is negative because it's pointing downwards. It's okay. Everybody is going to make an error. I've certainly made errors already today. So Vy is going to be less than 0. So let's say that V, I might write it as VAG, the y component, let's say is equal to minus 4 meters per second. And the x component is plus 1 meter per second. So writing it in equation form, I could write VAG is equal to 1 meter per second times x hat plus negative 4 meters per second times y hat. And of course, I could just write this as a single minus sign, that'd be fine too. Okay, so on your own, and writing it in a format like this, what is the numerical value of the bird relative to the ground? And I'm gonna, maybe before I do this, I will just give you the hint that maybe this is already obvious, but you can simply add together the x components and then separately from that, add together the y components. And before I release you to do this problem on your own, let's show that graphically. So let's do this tip to tail addition first. So here is VBA. And here is VAG. Let's see, let me get my numbers right. So this is supposed to be much longer like this, VAG. And so this is the resultant, that if I've gotten this right, 3 meters, pretty close anyway. So this is the resultant VBG, right, doing the tip to tail addition. So VBG is equal to VBA plus VAG. Let's check by canceling the inner subscripts. Yeah, we got it right. But I can also sort of concatenate a bunch of different things. So I can add 4 things together. So I could think of adding this vector, which is x hat times VBAX. I could add that together with this vector, which is y hat times VBAY. And then I can add to that, let's do here. So this one is y hat times VAGY. Shouldn't go quite so far down, should end about there. And then finally, I can add in x hat times VAGX, right? So I could write, so VBG, I can expand each of these, whoops. Here's my undo. There. I can expand each of these 2 vectors into their components. So I could write it as, instead of VBA, I could write it as VBA comma x times x hat plus VBA comma y times y hat. All of that, that's VBA. And then I have to add in VAG. So that's VAG comma x hat plus VAG comma y hat. And so adding those 4 vectors tip to tail would be this, whoops, shit. Would be this plus this plus this plus this, which gives us exactly the same as just taking the two vectors.
Can you explain what the red portion is?
The red portion, you mean this red portion or this red portion?
That one.
So this is VHE, the velocity of the air relative to the ground.
Mhm.
I've resolved it into its components. So this is the Y component, which is meant to be pointing straight down. And this is the X component, which is meant to be pointing straight to the right. It is another right triangle, yep. And so now I'm just adding 4 vectors together, 1, 2, 3, 4. And so now that I've done it that way, I can see, aha, I could rearrange this to just be VBA X plus VAG X, all that times X hat, plus VBA Y plus VAG Y, all that times Y hat. So when you're adding vectors together, if you got the components, it's very easy. You simply add the components together, and that gives you your new X component and your new Y component. So let's try it with this example. So given this VBA and this VAG, what is VBG? So work on that on your own briefly. And as soon as you feel ready, you can talk to somebody else.
Yeah, I just was not
Okay, Teddy, walk us through it, please. So I could write down here, hang on, listen up. So the velocity of the bird relative to the ground is equal to the velocity of the bird relative to the air plus the velocity of the air relative to the ground. Go ahead, Teddy. So 3 meters per second plus 1 meter per second. That's the X component. Go ahead. Good. So 2 meters per second minus 4 meters per second Y. So that gives us a total of 4 meters per second in the X hat direction. And what is this? Minus 2 meters per second in the Y hat direction. And if you look back at our drawing, you know, I was being a little sloppy as I made this drawing, but this describes a vector that's mostly pointing to the right and sloping downwards a little bit, which is pretty much what we got. Questions? Okay. Let's just do, let's do this. Sure. Concept test. So let's apply what you have just learned about relative motion to this question. So this is Hurricane Katrina, which you guys were all pretty young back then, but this was a big deal. This was like a lot of people died, a lot of people were strongly affected. Political careers were very strongly affected. Anyway, so it was a hurricane that hit straight on in New Orleans and caused a terrific amount of damage and chaos. But we are in the Northern Hemisphere, and for reasons that we probably won't talk about unless somebody really wants to, hurricanes go counterclockwise in the Northern Hemisphere. So this hurricane is spinning like this. So the question that's being asked, and the hurricane is moving this direction. So maybe I'll draw that in. The direction of its motion is like this. And so over here, over here, this is the right side of the hurricane because it's the right relative to the direction of motion. And so according to what's at the top of the slide, these areas are more likely to be hit hard by the winds of the hurricane than these areas. How come? See if you can explain that using this idea of relative motion that we've just been talking about. Think about it on your own, no talking yet. So again, remember that the whole hurricane is spinning this direction, counterclockwise. Okay, you can start talking it over amongst yourselves now. Let me just clarify one thing about this, and then I'll let you talk a little bit more. We're talking about when the hurricane makes landfall. So imagine several hours later, when the center of the hurricane has gotten here, it's still rotating like this. So it's going to be hitting with the center about here, and the rotation is going like this. Okay, go ahead and keep on talking. Okay, we're almost out of time. So listen up. I'm just going to introduce a little bit of nomenclature. So this we could call the velocity of this, let me use black, the velocity of the center of the hurricane relative to the ground. This point over here, that would be, I could draw that as the velocity of the right side relative to the center of the hurricane. And over here would be the velocity of the left side relative to the center. Okay. So I'll give you 30 more seconds. Try to use this nomenclature to answer this question. Why is there more damage on the right side than the left side. Go ahead and talk just a little bit more. All right. Okay, we are out of time, so we will finish discussing this at the beginning of class on Friday. Thank you.